Hello again, YouTubers. Dave out in Western Pennsylvania, USA. And these are preliminary studies of commercial graphite yarn. You can see that one is shown there. You can see the strands at the end. I'm using alligator clips for this series circuit. Of course, the loose connections can cause resistance, but we're not moving this around. We're doing bench scale work, so forgive me for the alligator clips. We have two supercaps in series. And what we've been doing, is you would learn from our videos, we're inserting graphite materials, graphite components in series with the supercaps, because we want to explore with our electronic device, electronic load, charges up to 4.8 volts. We're investigating the graphite materials. Here it's yarn. And if you unravel the yarn, it's commercially available, then you get the graphite fibers. And we're very interested in this graphite yarn or cord or twine. Very much interested in it because of the conductivity. And what you see there is a section of it. Here I have some dimensions. I'll put this in the description. The mass of the yarn there is 454 milligrams. The length of it is 97.3 millimeter. And the width, what I do is I try to tighten it up a little bit. I twist it to give you an idea, 7.4 millimeters. And what we do is run the step levels, power output, of the two supercaps without the graphite component. And then we insert the graphite component to see what resistance it's bringing to the table, so to speak. Now, these two supercaps I've had good luck with. They're commercially available from Amazon. They're rated at 2.8 volts, 100 farads capacitance. And way back a few months ago, we did an approximate measure of the capacitance, and we got about 95 farads. So they've been holding up very well. Now, I have them in series, so 2.8 times 2 is 5.6 volts. Now, I don't have resistors in parallel to each supercap, so the voltages are not balanced. I would not recommend going to 5.6 volts if you use these two. Stay under that. So we don't go higher than 4.8 volts, and that's where we've been going now, up to 4.8 volts. We want to investigate the graphite felt. It's not been cleaned. It was dry initially, used as is without cleaning in usually 95% ethanol, and we dry it to constant mass. And first we did a dry run, and then we did a wet run of the graphite, which is a deep eutectic solvent. Now this one, somewhat viscous, but a liquid at 20 degrees Celsius. We paint it with brush on a piece of paper towel. Now look carefully at that paper towel. And you can see I did a light deposition of aerosol graphite on that paper toweling. And I brush the DES electrolyte solution. The electrolyte is lithium bromide. Now we have to worry about the window of the bromide undergoing redox. That's another variable. But we're not using lithium iodide for several reasons that I will not discuss here. But we're getting the lithium bromide to dissolve in this DES. The DES is anhydrous zinc chloride with acetamide. And it's a 1 to 4 mole ratio respectively. And you warm that up, and it readily dissolves and forms a deep eutectic solvent. It's been staying a liquid for weeks at 20 degrees Celsius, and we can get, so far, 18% mass of anhydrous lithium bromide in this DES. So we have an electrolytic solution. Now you can form deep eutectic solvents that are reasonably conductive, but they're not cheap. This DES really is not conductive. That's why we have the lithium bromide in there. Now underneath, I just want to mention this to you viewers. I work with undergrads, and I like creating experiments for undergrads that want to get into energy storage, in this case, supercap, structure and function, components, material science. There are also home researchers that would like to get involved in supercap experiments. So this is for a wide community of viewers. My campus, I'll be retiring from teaching in June, but I will continue doing research. And our campus will very shortly be getting in a brand new scanning electron microscope, because we want to examine the graphite materials before and after experiments. And I want undergrads to get a basic understanding that supercaps require a conductive electrolyte, got to have ions there, the electrode material, and a separator, which could be paper to prevent a short. Now you can see under that paper towel, there is this material. I love trying different things when I go in a store. This was from Walmart, and this is refrigerator air filter. Now, on one side is activated carbon, accordion morphology, and on the back, paper. So I want to investigate that as an interesting source of surface area, the activated carbon, and the paper as separator on the other side. Now I've not used, I just have it there, laying there with the paper towel soaked in the DES and the yarn. But I'm thinking this could be very interesting because you have to have surface area. The yarn here offers decent conductivity, but you see graphite felt, which I work with, there's a problem with the thickness. And that thickness, I don't know if you can get it in focus or see it, that thickness can be a problem causing resistance. But it offers conductivity and some surface area. The yarn, well, I'm thinking we will coat some activated carbon in the DES on the yarn to boost surface area. And possibly this charcoal activated carbon, not charcoal, activated carbon, may be a very interesting component. In any event, we run the supercaps and do power outputs, and then we insert the graphite material to see the degree of resistance that it will contribute to the circuit. Now, what you see up here, and I'll post this data in the description and at my website. If you go to my website, I'm also an amateur artist. So you'll see some pretty off-the-wall designs that I do for relaxation. I hope you're not offended. I don't intend to offend anybody, but you might wonder why they're there. Well, I do artwork. Here you see some numbers. We did a charge, constant voltage, and we charge up the supercaps with or without the graphite. We've been going to 4.8 volts. Now, realistically, I'd like to design supercaps that would work at 3.7 to 4.0 volts, but I have to worry about the window, the electrochemical window of the DES. And, but bench scale, why not? We're going to 4.8 volts, and we charge a constant voltage, potentiostatic, with a trickle charge down to a cutoff of 0.15 amps. And according to what we're seeing, I've got numbers all over the place here. Generally, bring it up to 4.8 volts. And then the open voltage, we sometimes get right around 4.55 volts, open voltage before we start the step level analysis. So we start at 0.1 amp. We go up to 1.0 amp current draw. The cutoff voltage is 0.30 volts. Never want to go down to zero with the supercaps. In steps of 1/10 of an amp. And we've gone now to 20-second changes. And you can see here a run, which is this material shown. I did not seal it. We're just doing preliminary studies. And we got some good numbers, really. There are the numbers, index 1 through 10, going from 0.1 up to 1.00, 20-second intervals. There are the voltage drops, and then there's the power on the right in watts. So you can see we're doing maximum power output at index 5 to 6. That's about a half an amp, 500 milliamps. And then it drops down after that. But those numbers are not bad, considering that the DES is somewhat viscous, but when we ran it dry, it was just, the numbers were a little bit higher than that, but nothing to be concerned with. Now, running the supercaps alone, here are the numbers we're getting. I'll post these numbers. And there's your watts. Now, this would be the supercaps alone, 4.8 volts. And then the start, the open voltage, 4.67 volts. And you can see the numbers, 1 through 10, with maximum power output at steps 6 and 7, 1.9 watts. Now, those are pretty impressive figures. But of course, when I'm inserting the graphite component, that is going to be a source of resistance. And we want to cut that resistance down, but we have to have conductivity and surface area. Now we'll be doing with the graphite yarn nickel plating to boost conductivity, nickel cobalt alloy electroplate. We're going to deposit polypyrrole organic conductor. We're going to oxidize the yarn with permanganate, oxone, not ozone, oxone. I've seen some interesting results with that already. We're going to do sonication. And then I'm going to try to get some increased surface area. And I'm hoping that the nickel cobalt, will create contact points to boost conductivity even more. But I will also try this activated carbon material, and I will also apply a light paste in the DES electrolyte solution, finely ground activated carbon powder, and try to apply that to boost the surface area. Now, we're looking forward to examining scanning electron microscope images before and after runs. And we do cycles of charge-discharge. I've gone up to 300 cycles if you look at my other videos, and we'll be doing that shortly. And I want to get some evidence on whether the DES electrolyte solution is decomposing or we're getting dramatic changes as we go through cycles. Now, commercial supercaps, of course, they can run 500,000 or 1 million cycles of charge-discharge. But I am working with undergrads, and I want them to have a clear understanding of fundamentals before they go to work in the private industry or go to graduate school where they will be working with, let's say, much more expensive equipment. but it's important to have a basic understanding of the issues here, the important variables. I really like the yarn very much, and that's no surprise. Researchers are also investigating it, and I've got some other ideas, and I like sharing them, in most cases, with my viewers. So I'll post these numbers in the description, and at my website link, I will put more information, and that will be found somewhere at the bottom of page 6 of my website. And the aerosol deposition, aerosol graphite deposition, commercial spray, I'm looking forward to putting some of that on the yarn and just see if that increases some surface area, making a composite yarn. So there's a lot to do here. We also run these graphite samples with a power supply. I get these power supplies from Amazon, and they're very good, $35 US dollars. I don't pay shipping here in the US with my account. You could do constant voltage, constant current with this. And what we do is we set up with an LED as the load, electronic load, so you stay away from the heat, we get light. And I also will run samples. I didn't run this one yet, but I will put it in at 3.9 volts, potentiostatic 3.9 volts, and see if the current changes over 1 or 2 days of consecutive hours run. And if the voltage is changing, that means the resistance is changing. So we like to run that as well. And let's see if I can show you typical data. Yeah, that would be the 2 supercaps. The data for the 2 supercaps and the image. And here's a sample of that called yarn. So I'll be putting these graphs up. It's a very interesting project. Supercaps are, of course, very important. And we'll be looking at symmetrical ones, unsymmetrical ones, maybe down the road some pseudo-capacitors. But I like right now the yarn. Thank you very much for watching. Bye for now.